Thank you very much for the introduction and the invitation. It's my great pleasure to be here. So I'm going to talk about something in algebraic topology, namely homotopy groups of spheres. So here's an outline of my talk. So as a motivation, some geometric background. So I will discuss the story of smooth structures on spheres. So by the work of Kervaire and Milner, it turns out this has a lot to do with the computation of stable homotopy groups of spheres. So that's going to be my second topic. So I will introduce the definition and then talk about some historical methods of computing these groups. And then I will discuss some new method using something called motivic homotopy theory. So motivic homotopy theory is a theory that was designed by Wolski and Morel to use abstract homotopy theory to study problems in algebraic geometry and number theory, and it has been very successful. So recently we discovered that this theory can also be used to study problems in classical topology, namely the computation of homotopy groups of spheres. So I will discuss about that. And if there are still some time left, I will discuss some future directions. So let me start with, as a motivation, the famous Poincaré conjecture. So in 1904, Poincaré proposed the famous conjecture of the famous question, namely the following: if M is a closed manifold, closed here means no boundary compact, and it's of dimension 3. And further, suppose that pi 0 and pi 1 are all 0, namely it's path connected and it's simply connected. Then the question is M homeomorphic to the 3 sphere? So as we all know, the answer is yes. This is solved by Pellerman in 2002-2003 using geometric analytical methods. So one way to try to understand the statement of Pellerman's theorem is the following, which is what is this condition doing here, being simply connected for a closed 3-dimensional manifold? So if you think about it, this condition for a closed 3 manifold is equivalent to the condition that this manifold is homotopy equivalent to the 3 sphere. So in other words, this theorem is saying that if a manifold is homotopy equivalent to the 3 sphere, it actually implies that it is homeomorphic to the 3 sphere. So being homotopy equivalent is a weaker equivalence relation compared to being homeomorphic to the 3 sphere. So the weaker one actually implies the stronger one. So of course, we don't have to ask this question just in dimension 3. We could ask this question in all dimensions. Namely, if we have an n-dimensional closed manifold, topological manifold, which is homotopy equivalent to the n-sphere, is M actually homeomorphic to the n-sphere? So for dimension 1 and 2, it's not hard to see the answer is yes. It turns out the answer is yes for all dimensions. So the n equals to 4 case is proved by Friedman in the 80s, and the higher dimensions is proved by Smeyer, Newman, and Cornels in the 60s. The version Smeyer proved need to require this manifold to have a smooth structure to start with. So in summary, for spheres in all dimensions, being homotopy equivalent, actually, this weaker equivalence relation actually implies the stronger one, being homeomorphic to the n-sphere. All right, so what about in the smooth category? So what if the manifold we start with also have a smooth structure to it? There's the even stronger equivalence relation, namely being diffeomorphic to the standard n-sphere sitting inside of Rn plus 1. So we could ask this question: if we have a closed smooth n-manifold, which is homeomorphic to Sn, its underlying topological space is Sn, is M diffeomorphic to the n-sphere? So in other words, could the topological n-sphere has exotic smooth structure? So it turns out when n equals 3, the answer is yes. This is known a long time ago, in the 50s. So it turns out every topological 3 manifold has a smooth structure and it is unique. So in particular, the 3 sphere has a unique smooth structure. So the n equals to 4 case is still open. This is the smooth Poincaré conjecture in dimension 4. And it's wildly open. For high dimensions, well, it turns out in dimension 5 and 6, the answer is still yes. But in even higher dimension, by the Kervaire and Milner, as we all know, Milnor discovered this exotic 7 sphere. But in general, work of Kervaire-Milnor discovered that this phenomenon of exotic sphere happens quite generally in high dimensions. So with that in mind, we could be further asking in which dimensions there is still a unique smooth structure, or when we fix the dimension, how many smooth structures are there on a given n sphere. So the second question was actually answered by the work of Kervaire-Milnor in the following sense. So I'm going to give a summary for Kervaire-Milnor's theorem, and this requires n to be at least 5. So let's consider theta n, which is the set of smooth structures on the n sphere. So if we think about the operation connected sum, it actually gives us a group structure. So by the theorem of Smeyer, this corresponds to the H cobordism classes of homotopy n spheres. So homotopy n spheres just means manifolds which is homotopy equivalent to the n sphere. So cobordism means something in one higher dimension whose boundary is a disjoint union of two spheres. H here stands for homotopy, requires that the inclusion of the two boundaries is a homotopy equivalence. So by the theorem of Smeyer, this group of smooth structure on the n sphere is the same thing as H cobordism classes of homotopy n spheres. So there is a subgroup, which I call it theta n BP. These are the homotopy spheres that bound parallelizable manifolds, which just means the tangent bundle are trivial. So here's a summary of Kervaire-Milnor's theorem. So first of all, this subgroup is always a cyclic group, and its order is almost known up to a factor of 2. So when n is even, this is always a trivial group. When n is 4k plus 1, this group is either the trivial group of or the group of order 2. When n is 4k plus minus 1, the order of this group has something to do with the Ballooning numbers. So for the purpose of this talk, let's just say this is in general a huge number. Okay? So in particular, when n equals to 7, I believe this number is 28, and it goes up very fast, as you can see from this expression here. Okay, so this subgroup, we understand it very well up to a factor of 2. So later on, you will see that this factor of 2 have something to do called the Kervaire invariant problem, which I will mention later. So how to connect this subgroup to the whole group? So there is a short exact sequence. So this being a subgroup, and there's a description about the difference. This is something called pi n mod j. So pi n here is the nth stable homotopy groups of spheres, something from algebraic topology, which I will define and explain later. And j here is something called j homomorphism. It's a map from the nth homotopy group of the infinite dimensional special orthogonal group into the nth stable homotopy groups of spheres. It's actually a direct summand. So this just means the co-kernel of this part. So j part is something which is very well understood. Okay? So a summary here is that if you want to understand how many smooth structures on the n sphere, namely the order of this big group theta n, we already know what happens to this subgroup. All we need to do is to compute this co-kernel of j part. Okay? So in this sense, Kervaire-Milnor has reduced this problem of counting smooth structures on the n sphere to a computation in algebraic topology. So that's what happens when n does not congruent to 2 mod 4. When n does congruent to mod 4, it's slightly more complicated. So this short exact sequence becomes a long exact sequence. So after this co-kernel of j, there's another group homomorphism to z mod 2, and this theta bpn minus 1. So every group homomorphism into z mod 2, there's only two possibilities. It's either this map is 0, which happens in most of the dimensions, or this map is surjective. In either case, we can decide what happens to this group. This is the ambiguity in the previous slides about this order 2 thing. And this map is called the Kervaire invariant. So the Kervaire invariant also have a very interesting geometric story. I'll just say a little bit about it. So using his invariant, Kervaire first discovered a manifold in dimension 10, which does not emit any smooth structure. So later on, by the work of Kervaire-Milnor, this invariant has a lot to do with smooth structures on a given manifold and etc. So in particular, there is a famous question, which is the Kervaire invariant problem, asking when this map is is non-zero. And here is the summary of what's known about the Kervaire invariant. By the theorem of work of Browder, Barajos, Mahawar, Tangara, and more recently Hill, Hopkins, Ramino, this map is almost zero in most of the dimensions, with the exception of these 5 or 6 numbers. So these numbers are 2, 6, 14, 30, 62, and possibly 126. The status of 126 is still open as of today. And these are all numbers 2 less than a power of 2. So one thing I'd like to mention, which I think is particularly interesting about dimension 62, is the following. So the Kervaire invariant is about some abstraction class. And there's for defined free manifolds. So in dimension 30, John Jones, in his thesis, he constructed an explicit manifold with Kervaire invariant 1, namely its map being non-zero. But since this is a group homomorphism, that means if there's a manifold of Kervaire invariant 1, that means exactly half of the manifolds, free manifolds, in that dimension will have Kervaire invariant 1, the other half of 0. The 62 result is still a homotopy theoretical result, in the sense of until today, no one has been able to construct an explicit manifold in dimension 62 of Kervaire invariant 1. Although we know half of the manifolds in that dimension has Kervaire invariant 1, which I find very interesting. But of course, the problem is we don't really know how to explicitly compute the Kervaire invariant. That's the problem. Okay, but anyways, so the summary here is that the work of Kervaire-Milner reduced this problem of counting smooth structure on n spheres to 2 problems. One is the computation of stable homotopy groups of spheres. The other one is the Kervaire problem, which is almost solved except one dimension. All right, so let's get back to the other question, namely for which dimensions it could still have a unique smooth structure. That may be an easier question to answer. So a necessary condition would be the subgroup should have order 1 to start with. For n equals to 4k minus 1, it is never unique. Recall that this has something to do with balloon numbers. So in dimensions, say 15, this number is huge, like 16,000 or something. For n equals to 4k plus 1, it depends on the Kervaire invariant problem. We have a long exact sequence. So we want this group to be the trivial group, then we need this map to be non-zero. And namely, the Kervaire invariant has to be non-zero in the corresponding dimension. And we just learned that in most of the dimensions, this map is actually 0. So combining 4k minus 1 and 4k plus 1, that's all the odd dimensions. So all dimensional spheres that could have a unique smooth structure, the candidates are exactly 1 less than the dimension of the Kervaire invariant 1 problem. And namely, these dimensions. There are 3 less than power of 2. So what do we know about these spheres? For dimension 135, they are known to Kervaire-Milner. For 1329, we know they are not unique. This is done in Peter May's thesis. And we know exactly there are 3 smooth structures on these 2 spheres. For dimension 125, we do not know how many smooth structures are there, but we do know it's not unique. This is done through the study of something called the spectrum of topological module forms, which is a generalized cohomology theory that can be used to detect certain maps between spheres. And for the remaining dimension 61, that's the theorem of Gordon Wang and myself. So we did a computation in algebraic topology. We computed the 61st stable homotopy groups of spheres is 0, and therefore the 61 sphere has a unique smooth structure. So combining based on earlier work, the corollary is that only odd dimensional spheres with a unique smooth structure are just 1, 3, 5, and 61. So 61 is actually the last one. So you may ask, okay, so that's the story for odd dimensions. What about even dimensions? So what do we know about even dimensions? Well, so first of all, this subgroup doesn't give us anything for free because it's always the trivial group. We cannot rule out any dimension. Based on our computation, we made a conjecture. So for dimension I6, so we do not know anything about dimension 4. So only even dimensional spheres with a unique smooth structure are just 6, 12, and 56. And we already know these 3 cases. The first two were known to Kervaire and Milner. 56, it was recently known by Isaacson, also a computation in algebraic topology. So the conjecture is more about there's no more. So for the no more part, there has been some progress by the work of Barinsky, Hopkins, Mahoward, and Quigley using something called chromatic homotopy theory, which is a theory to study periodic phenomena in homotopy theory. They confirm that for the even dimensions over 50%, this conjecture is true. And of course, we want to do this toward 100%. So I have some ongoing progress with Barons and other people also using chromatic homotopy theory. I'll say a little bit about what that theory is about and some flavor about it, but yeah. So next, I'd like to talk about homotopy groups of spheres, and any questions before that?
So what's the precise statement that more than half, this last statement is more than half is known?
Right. So for some explicit dimension congruent to 192, so more than 50% of these numbers, we know it's not unique.
So in other words, you're saying that out of, if you cut off at some fixed bound, more than half of them?
So here's what I mean, right? All the even numbers can be written modulo 192 into like these numbers. And for, say, we can rule out half of these numbers. Yeah. And this periodicity is due to TMF, which is an analog of real K theory, which is aperiodic. We have the real Bott periodicity, but there's some higher analog of that. Yeah. All right. So homotopy groups of spheres is something in mathematics which is very easy to define, but actually very hard to compute. The definition is very simple. We consider based continuous maps from spheres in dimension n plus k to dimension k, then we model by homotopy. This turns out to be an abelian group. So what do we know about these groups? When n is smaller than 0, this group is always a trivial group. When n is 0, this group is just z, the integers. And we know exactly what are the copy of z's in here. They're always finitely generated abelian groups. And Sarah computed the rational part, namely there's only finite many of these many of copy of z's, and all other bi-gradients, these are just finite abelian groups. So which means that we can compute one prime at a time and sum them together, if we like. So here's the table for some low-dimensional computations. So, so the columns are when we fix the target sphere. Okay. So for example, this column here is just the homotopy groups of S1. So namely because its universal cover is contractible, so there's no higher homotopy groups. But even focus on the 2 sphere. This is pi 2 of S2, that's Z. This is pi 3 of S2, that's a Z. That's a pi 4 of S2, that's a Z mod 2. So infinity means a copy of Z. This means, these numbers means a Z mod 2, Z mod 12, and so forth. Then when we see like a square, that means Z mod 2 plus Z mod 2. And this means Z mod 24 plus, direct sum with Z mod 3, and so forth. So you can already see the groups showing up are kind of random, kind of complicated. But there are some patterns, right? For example, if you compare these two lines, S2 and S3, they have almost identical homotopy groups. That's just because of the Hopf fibration. There's only differed by this number. But there's another phenomena. So if we start with the diagonal and you look into the right, you see they eventually becomes the same group. They stabilize. For example, so the stabilization is, this one is the difference of these 2 dimensions, right? So when this n goes up, they eventually all become Z mod 2. And the second eventually all becomes Z mod 2, Z mod 24, 0, 0, and so forth. So starting from somewhere in the diagonal, and each line stabilizes. So this is called the stable phenomena. So there's actually a theorem by Frieden saying that these groups only depends on the difference of the dimension when this number is large enough. Okay? And we call this the nth stable homotopy groups of spheres, or simply just pi n. So Sarah told us these are always finite abelian group, so we can compute one point at a time and then just sum them together. And if we combine all the gradients together, it has a richer structure. So first of all, it's a graded ring, because if we take two maps and the difference of dimensions are L and M, we take the composite, the difference of dimension will be L plus M. So this is a commutative ring in the graded sense. There are also higher products. So if you're familiar with massive products, there's something called total brackets in the topological setting. So we input 3 maps. The composite of the consecutive two are 0 up to homotopy, then we can output a total bracket out of it. So when we do these computations, we would like to understand these higher structures as much as possible, because it helps. And here's a table of what we know for the stable stems. There's only one grading, but just because I want to list the first 55 stems, so I listed it in this way. And as you also can see, the groups showing up is kind of random. There are a few zeros, but not many. There are some groups which I have underlined. That's the contribution of the J homomorphism. And that's well understood up to infinity. Okay? And basically, what we know is like all primes will show up. All kinds of finite abelian group will show up eventually somewhere in this table. So before our work, we know this table around this range, 40-something, 50-something, but now we know roughly double the range. We know 90, around 100 using some new method, which this is something I'm going to talk about. Okay, and here is another way of picturing these computations. So let me do this. Maybe I'll draw something on the side. So I'm showing a picture in 2 dimensions. And you see a bunch of dots and connecting by lines. So this is supposed to give you some idea of how the groups look like. So this is a picture for p equals to 2. Maybe I would just draw something by hand. So I'm drawing some dots and some line segments on the board. So each dot here means a sigma 2. Okay, so let me just do that. So this is a way to visualize the group structure. So each dot here means a sigma 2. Okay, so in the first column there's only one dot. So that means pi 1, the stable pi 1 is sigma 2. So pi 2 is also sigma 2. So this is a 2 primary thing. So in here I have 3 dots connecting by lines. So instead of 3 copies of sigma 2, I have a sigma 8. So these vertical lines just means group extensions. There's nothing in 4 and 5. That means these groups are both 0. This is a sigma 2. This is a sigma 16. There's no lines. So that's a sigma 2 plus sigma 2, and so forth. Okay. So just to give an idea to visualize this thing. But I also mentioned that there is a graded ring structure. Okay. So some other lines. So for example, this line of slope 1 here. This dot has a name called h1. So if I draw another dot connecting it to h1 using the slope 1 line, so that means this dot is h1 squared, and this dot is h1 cubed. And this dot's name is h2. So vertical line means 2 extension, but also means multiplication by this dot h0. So that will be h0 times h2. This will be h0 squared times h2. And they go into the same dot. That means multiplicative relation. Okay, so this picture is trying to visualize part of the ring structure as well as the additive structure. Okay, so the picture I'm trying to show you is a picture up to say like 90. So you can see some global phenomena. So first of all, there's no dots above this line around the slope of 1/2. And near the edge of 1/2, you see a lot of patterns like this. You can probably see this vaguely. They're 8 periodic. They are the contribution of the image of J. So they are, roughly speaking, related to the J homomorphism, the contributions from Lie groups. So we have some patterns in here and so forth. And between this part and this lower part, there's a big gap. Okay, so this is only a picture. There's nothing in this range. Okay, so this picture is only up to 90. If you were to have a picture, say up to 1,000, you're supposed to see a lot more gaps. Okay, so the whole thing looks like a rainbow, a bunch of layers. So this is what chromatic homotopy theory is about. Namely, every element in this ring fit into a periodic family. And this vertical one is the rational part. And this is the first layer, that's the J part, has something to do with the Lie groups. Then the second layer has something to do with topological module forms. That's the high 2 part. And you're supposed to see a lot more layers later on. Okay. So, so by the way, part of the idea to target this even dimensional sphere conjecture is to establish enough family, non-zero family, because each dot fits into a periodic family. So in the end, the hope is to cover all the dimensions and prove that conjecture. And okay, any questions or comments about this picture?
You have the different colors for different areas.
Right. So these are some multiplicative extensions, basically. Yes.
Can you just correlate that picture with what you've just drawn on the board?
Oh, yes. That's just the first, this part. Up to here, this corner is this. I'm just drawing this picture up to like, yeah, over here. But this picture here is supposed to be like up to 90. Yeah. I'm sorry, this picture is not looking very. Yeah. Yes. And I didn't explain what the vertical line means. So roughly speaking, it's something called the Adams filtration. So basically, it states that as a map between spheres, if you can decompose this map into several maps such that each map induces trivially on homology. Okay? And the maximal ways of doing that. And of course, that's not just the picture, it should be just the E-infinity page of a spectral sequence. And that's the whole spectral sequence picture. So again, so if you're not familiar with spectral sequences, the way it works is it's like a chessboard. Like in the beginning, we have a lot of dots. And the rule is whenever we have a differential, we cancel the source and the target, and we have some leftovers. And in the E-infinity page are the leftovers. That's the answer we're looking for. So in this picture, in the first 13 stem, there's no differentials. Starting from here, we have D2 differentials and D3 differentials. So pi 14 instead of Z mod 4 plus Z mod 8, because these 3 dots are killed. So we only have 2 dots left. So this is just Z mod 2 plus Z mod 2. And 15, there's only 5 dots left, plus this one. That's a Z mod 32 plus Z mod 2, and so forth. So the hard problem, so the way of computing these groups are various spectral sequences. And it's a relatively simple question to figure out what the E2 page is, but it's much harder to figure out how the differential works.
How many pages are you looking at here?
I'm stacking all the pages on one picture, right, because the difference of the differential are determined by the length. So a typical differential in this picture is always going to the left by 1 and going to up by r. So the starting point is E2 page. And that's the first D2 differential. It's going to the left by 1, going up by 2. And that's the first D3 differential. So I'm just stacking all the pictures together. So these 2 dots will no longer exist on the E3 page. But the rest still are. And these 2, there's a D3 happening here, making these 2 dots disappear on the E4 page, and so forth.
So it runs sideways.
Yeah, right. Right. And the picture I just showed you before is the leftovers. You see a lot of gap over there, but on E2 pages there are a lot of things in between.
How many steps before it degenerates in this region?
Well, as we understand, there are different of infinite, arbitrary long lengths. I think now it's a theorem. We do know it doesn't degenerate after a certain page.
But
That's the answer.
in terms of the region you're not drawing the entire.
The longest one is D7, I believe. Yes, so E8 is infinity in this range. Yeah. All right. Okay, so I'm going to talk about some special sequences, but I will try to focus on the idea instead of the actual computation, the technicality, I mean. So Serre first used the Serre special sequence computed up to A stem, and he actually computed the unstable range, the bigrid one. Then Toda used the EHP special sequence computed up to 19 stem. So later on, if you just want to focus on the stable stems, the two most popular special sequences are the Adams and the Adams-Novikov. So they have something in common. They both converge to the p primary part of the stable stems, because we can compute one point at a time. The E2 page is always some X group over some Hopf algebra or Hopf algebroid, depending on different homology theory. So for the Adams one, it's depending on the mod-P homology. And in here, it depends on the complex cobordism spectrum. Okay? So before I explain any computations, there's a warning. This is something called the Mahoward uncertainty principles. So first, Mahoward's uncertainty principle states that any special sequence converging to the homotopy group of spheres with an E2 page that can be named using homological algebra, the previous two are both such special sequences, will be infinitely far from the actual answer. So meaning that this is not an algebraic problem. We need methods to compute the differentials. You need topological input to actually compute the differentials. E2 page is fine. That could be something homological algebra that can be done by a computer program, but differentials, not so much. So based on my experience with Malcolm Howard, I propose the second Mahoward uncertainty principle, which states that any method that computes these non-trivial differentials in such a special sequence will leave infinitely many differentials undecided. So when I first started as a grad student, I asked Malcolm Howard, so there are so many special sequences, so many methods computing these differentials, what is the best method? The answer was, well, there's no best method. You really have to combine all the known methods in order to push forward the known range a little bit. So that's basically the spirit. And of course, these are just principles. They're not theorems or anything like that. Okay. But I hope I give you the feeling that computing these differentials are the real hard work and is highly non-trivial. Okay, so now we have at least two methods. We should try to compare them. So one comparison is through the term reduction, which preserves by degree. But it turns out this method is not very useful in practice. There's always this phenomenon called jump-off filtrations. Because they're given by different filtrations, so something surviving here may correspond to different filtration here, so therefore it's not connected by this degree preserving map. But luckily, but also more complicatedly, there's another connection. This is developed in Hinz-Miller's thesis, which I call the Miller square. So it turns out these two E2 pages, there are two other special sequences. So about to a bigraded converting to a single grading. Then here we have a trigraded term using two other special sequences converting to the E2 page of these two things. So now we can make an even richer connection by going all the way to here. But I want to make some comments about this picture. So the above two are more topological in flavor. They are guided by the uncertainty principles. We might have ways of computing the E2 page using algebra, but we need topological input to computing differentials over there. But the lower two are more algebraic in nature. We can even write a computer program to compute in any range we like, well, in a reasonable range we like, all the differentials up to that range. And also at all primes, this Cotton-Allenberg one collapses at all primes. So that's also an interesting feature in this picture. So Miller developed a method computing D2 differentials in this bar sequence using D2 differentials in this bar sequence. The point here is that this one is algebraic in nature and that one is not. So using this method, Miller systematically produced a lot of topological differentials over there and is very successful. Later on, I will explain how to use multiple homotopy theory to generalize this technique. All right, so having said that, so what do we actually know? When p equals 3, we know around 108 stem. When p equals 5, we know around 1,000 stem. So if you think about it, these two numbers are both the expression of p cubed times 2p minus 2. So in this sense, we know about the same range in these two dimensions. Part of the reason is that the spiral sequence, all the generators, algebraic multiplicative generators, the degrees have something to do with p. So when p is large, this spiral sequence is more sparse, making it easier to compute. So in that sense, we know about the same range. But if you plug in p equals 2, this number is only as small as 16. So in that sense, we know a lot more about prime 2 than other primes. So now I'm going to focus on prime 2 computations. So the E2 page is done in Peter May's thesis using something called the May spiral sequence. Using Toda's computation and things like Leibniz rule, he computed the stable stems up to the 28 stem. So later on, Baird, Mahover, Tangara computed up to 45 stem, playing around with Massey product Toda brackets, and there are also some tricks to do that. So there are other methods such as using power operations by Brunner and so forth. So more recently, Isaacson started to use motivic homotopy theory and computing the motivic atom spiral sequence over the complex numbers and have very solid computation up to 59 stem. So in 2017, Wang and myself, we developed this RP infinity method, computed 2 more stem. So the point here is that each method will get stuck, and then we need some new method guided by the second principle. But we also get very stuck using this RP infinity method. But then we realize there's something even stronger in the motivic setting. We call this the motivic Couvertin method. So the theory is developed by Gregory, Wang, and myself. Computations are done with Isaacson, and we have recomputed the previous computation, and also the new computation up to 90 stems with very few exceptions. So I would say this is by now the most powerful method. And even recently, we have some ongoing progress towards the last Kervaire invariant problem in dimension 126. This is joined with Lin. All right. So this is roughly speaking the range I mentioned earlier. The starting Sire, Toda, May, and then Baird, Mahover, Tangara. So the geometric application I mentioned earlier about the 61 sphere is just saying that in the end, this column, there's no dot left. And therefore, the homotopy group is 0, and the smooth structure is unique. And now we have computing into a much larger range, and so forth. All right. So I'd like to say something about the motivic homotopy theory. Any questions before that? All right. So motivic homotopy theory, so the new method, new input is motivic homotopy theory. So as I mentioned, motivic homotopy theory is a mixture of algebraic geometry and homotopy theory. It was designed to study problems in algebraic geometry and number theory, and it was very successful by the work of Wolski, such as the solution of Blockato, Billingson-Lynchstrom, etc. But we realized you can also use that to study problems in classical topology. So for notation, SH is my name for the stable homotopy category. So objects in here are spectral or generalized cohomology theory, if you like. Also, topological spaces are in here if you stabilize them. So motivically, there is a such stable homotopy category for any field. In the stable homotopy category, we have a single gridded sphere. But in the motivic category, there's another type of spheres coming from the algebraic geometry. The essential one is this affine line minus the point, or GM, which we denoted by S1, 1. The topological simplicial sphere S1 is called S1, 0. If you smash them together, you get the P1. So these bigridded spheres, if you invert them, you get the stable category. And as a result, you have bigridded motivic homotopy groups, motivic cohomology groups, and all other things. So for example, one very good thing about the classical stable homotopy category is that taking cohomology is a representable functor and is represented by something called the Eilenberg-MacLane spectrum. So motivically, Wolski defined this motivic cohomology and also constructed this whole category, and that functor is also representable and is represented by this motivic Eilenberg-MacLane spectrum. You can also study like algebraic key theory are represented in here and so forth. But just as a result of the two types of spheres, everything are bigraded. In comparison to classically, it's a single grading here. So upshot is that all the classical computational tools, they all exist in the motivic setting. Okay, so in particular, we can also define the motivic stable homotypic groups of spheres, bigraded. So why do we care? What's the motivation here and what do we know? So Morel proved that for arbitrary base field K, the n comma n motivic stable homotypic groups of spheres are the Mueller weight K groups. And work of Roding's, Spiesweg, and Ossphere, they show that n plus 1 comma n and n plus 2 comma n of these groups can be expressed in terms of motivic cohomology, Hermitian and Mueller K groups of the base field K. So in this sense, you can think that these groups are generalizations of some arithmetic invariants of the base field. And that's about what we know for the global structure in the sense of independent of the base field, like a general description for the base field. But for a specific base field, what we know something about over C over R and over finite fields in these ranges. That's about what we know for these groups. And of course, from my perspective, my interest in this is its connection back to the classical stable homotypic groups of spheres. So why there is such a connection? The reason is the following. So if you take a complex variety and we take the C points, we get back to a topological space. So this construction is called the Beatty realization, and this functor can be extended to the whole stable homotypic category. So Wolski proved that the homology of a point in the complex motivic setting, this is a motivic homology of a point, instead of just Fp, mod P coefficient, instead of just a single copy of Fp, it's a one generator polynomial ring, and this tau is in degree 0, -1. So this is actually a highly non-trivial theorem equivalent to Black-Cottle. So this element tau can actually be realized as a map between two bigraded spheres. So know that we already invert both spheres, so we're allowed to have negative gradings. So this is a tau correspond to a map between two completed spheres. So in homotypic theory, we can complete at a prime to just a topological space, not just for any rings. And this map tau, after this Beatty realization functor, becomes the identity map. So work of Dr. Addison showed that if we invert tau, so all the modules over the sphere, namely the whole category, is the same thing as the classical stable homotypic category. So if you invert tau, the motivic homotypic category becomes the classical stable homotypic category if we complete at a prime P. And in particular, if we invert tau for the bigraded motivic stable homotypic groups of spheres, we get back to the classical stable homotypic groups of spheres. So all the tau-free part corresponds to the classical information. So new information is actually the tau torsion part. But if you mod out by tau, that's the cofiber of tau, that's a two-cell complex, but also an E-infinity ring spectrum. So Isaacson observed that there is a motivic Adams-Novikov sparse sequence for this two-cell complex. It just collapses for degree reasons. And as a consequence, we have a global description for this two-cell complex. Its bigraded homotypic groups is exactly that description in homological algebra. So this is a very surprising fact because classically, the sphere is like a single stable cell, and its homotypic group is already very complicated. But motivically, this two-cell complex, we have a complete description in terms of algebra. So having this isomorphism, there are two complicated spectral sequences converting to them. One is algebraic Novikov, something classical algebraic, and one is the motivic Adams, which is more topological and motivic. So Isaacson computed right-hand side up to 60 stem, and my collaborator Gordon Wang made a computer program computing left-hand side algebraic spiral sequence around 45 stem. And when we compare these two computations, we know they converge to the same thing. But they have the same data starting from the E2 page with all the differentials. And that shouldn't be a coincidence. So in fact, the three of us prove that these two spiral sequences are isomorphic, starting from the E2 page, all the pattern of differentials, of course, the abutments. So, and there is a theoretical explanation for this. So if you think this element tau in the homology of a point as a deformation parameter, we prove that there is an equivalence of stable infinity categories. So the left-hand side are just cellular modules over this two-cell complex. Okay, so it's an E-infinity ring spectrum. The right-hand side is a derived category of comodules over this Hopf algebroid, which through the work of Quillen and Morova is also known as the category of cosine coherent shifts over the module stack of one-dimensional formal group laws, which is something chromatic homotopy theory is built up upon. So there's also alternative proofs by Cross and Piv-Strugovsky. So one way to think about this statement is following. And if you don't like stable infinity categories, you can use triangulate categories. You can think this tau as a parameter of a deformation of stable infinity categories. So in the middle are the information for the multiplic homotopy category over C. If you invert tau, you get back to the classical stable homotopy theory. But if you mod out by tau, you have this explicit algebraic category, which is just the derived category of certain abelian category. And then the isomorphism of spiral sequences are just identifying this category as purely algebraic and to translate over there. And then we can use this deformation of categories to play with deformation of spiral sequences. So recall that earlier on, Mueller has this technology producing topological D2 differentials using algebraic methods. But now, since we have a deformation of categories, we have the corresponding deformation of spiral sequences. Then if we start with any differentials on the right-hand side, we first identify it as the algebraic Novikov differential, which is something purely algebraic. There's a computer program to compute it. Then we lift it back in the middle and push it forward to the left using the Beatty realization. Then we get back information in the classical spectral sequence. So therefore, through the motivic word, we can translate classical algebraic Novikov D2 differentials. Now we obtain some classical topological Adams differentials. So the stepwise computations requires a lot more computation by computer programs, such as computing the E2 page in the motivic setting, and etc. And there's also a lot of ad hoc arguments classically, but the real essential part is to identify this algebraicity of this category in between. So we can reprove many historically known hard Adams differentials using this method. I listed a few proved by various authors using various different methods, like May, Mahar Tangara, etc., using all different methods. But they can now all be used to prove by this motivic covert method. So in particular, the last differential proved by ourselves in the 61 stem, so that differentials, it took us 40 pages to write down the whole argument. But now it's just a one-line proof. It's output of a computer program, and then we just do the naturality thing, then we got it. And it also recomputes early range very effectively. So this is a big picture, unfortunately, but I marked a few differentials which are historically harder to compute with. I marked 6 of them. And this is the motivic output. And so all of these data are computer outputs. So there is a D2 differential there. So that's 1 out of 6. There are 2 D3, so that's 3 out of 6. So it's a D4, that's 4 out of 6. There's an extension can be translated into a differential, that's 5 out of 6. So basically, this motivic method computes 5 out of 6 of the harder differentials in the range up to 45. So that leaves 1 left. So that's okay, because it does not violate the second Mahar uncertainty principle. So that differential cannot be computed using the motivic method, but we do know a lot of other methods computing it. So since I have time, I will say a few words about future directions. So these computations are mostly done over the complex numbers. We could be asked, can we do this over a general base field? So that's one direction. Another direction is we not only want to study stem-wise computation, but we also want to study some large range phenomena in the spiral sequence. So for the first one, let me just mention that over C, there is a simple deformation, and there's a parameter. But this tau does not exist in general for a Motivy cohomology of a point over an arbitrary base field. For example, over R, it does not exist. So instead, we joint work with Bachmann, Koh, and Wang. We introduce a T structure we call the Chow T structure. And we can have some similar algebraic statements of the whole stable infinity category, and then there's a more complicated tower. This is the Posnikov Wetthead tower. So we can use this T structure to truncate the sphere into a bunch of pieces. Each piece lives in the heart, which is an abelian category. We have the complete description of its Motivy homotopy groups, but then we can do this zigzag thing, playing with naturality, even on the spectral sequence level, and try to deduce differentials to the sphere. The point here is that all the pieces, they're completely algebraic. They therefore can be computed by computer programs for general base field. But it's more complicated than just a deformation. You actually have a tower for it. And for some general range phenomena, so one thing I like to mention is that in algebraic topology, there's this Hopf invariant problem, there's Kervaire invariant problem, and they're all closely related to the atom spiral sequence. So in the atom spiral sequence on the one line, this is the first line. So these elements actually, they have a name. They start with H0, H1, H2, H3, and the H4 in here, and so forth. So that's the complete information for the one line. They're generated by these classes Hj, with the property that Hj cube Hj to the fourth is 0 starting from H1. So atoms prove that in this spiral sequence, only the first few up to H3 survives in the spiral sequence, meaning that they don't support differential, they're not killed by any differential, so they are the leftovers on the E-infinity page. So they correspond to homotopy classes. But only the first until H3. Starting from here, it supports a differential. And this one has a topological interpretation. This statement is equivalent to that the tangent model over the n sphere is trivial if and only if n is 1, 3, and 7. The first two are Lie groups, but at 7 also the tangent model is trivial. And more recently, Hill-Hopkins-Ravenel, they resolved the Kervaire invariant problem, which can be translated to the survival of this Hj squared. That's H1 squared, this is H2 squared, and this is H3 squared, and so forth. So the two lines are more complicated, but the survival of these particular classes, they actually prove that up to j equals smaller or equal to 5 and positive 6, they all survive, if and only if. The later ones, they do not. And this is equivalent to there exists a free A manifold with Kervaire invariant 1, if and only if, and it are these numbers, and possibly 126. So one may ask, what happens to Hj cube? So recently, Berkland and I proved that, again, only the first few survives, and later ones they do not. So Hj cube survives even only if j is smaller or equals to 4. So we have some ongoing progress to interpret this in terms of free manifolds. And but you note that Hj to the fourth are 0, fourth power. So what's next? So don't worry, because there are so many other families. They all should have certain free manifold information. So in fact, in X, there is this operation that preserves this filtration but doubles the total degree. And in particular, if I take square 0 to these classes, they correspond to some kind of Frobenius action in the Kervaire complex. But anyways, so we can define something called the square 0 family so that Hj square, and J cube are all such families. There's a conjecture called the new doomsday conjecture. It's called new doomsday because the doomsday conjecture was false, and there is a new doomsday conjecture. But anyways, so conjecture states that for any non-zero square 0 family, only finite many classes survive. So it was the case for the Hopf, Kervaire, and the Hj cube situation. The one-line situation is equivalent to the Hopf invariant 1 problem. The two-line situation is equivalent to Kervaire invariant problem. And that's a type of the 3-line here We know what happens to HJQ, but there are still a lot of other many cases remain, and we do not know what happens to them. And based on our experience, we also propose something called the uniform doomsday conjecture, which gives a specific statement about how these families should die eventually, which is satisfied for all the known families, but is still wildly open. So I will stop here. Thank you.
Any further questions? I did not understand any of the bigraded notation that you were using. Could you explain what you have?
It's just in this category compared to the classical stable homotopy category, which has a single grading. Yeah. This category, we have another type of sphere. We just use that as a second grading. So we can just smash them together and map it to whatever space we already have. Yeah. Mm-hmm.
Related to that, can you describe what like S01 looks like? Or maybe S02?
In a sense, you just shift the grading formally. Because in the stable homotopy category, we invert both types of spheres, so we're allowed to just shift.
Okay,
yeah.
Okay.
Yeah.
So I just understand P1 and GM.
Right, it's like the classical situation. We can talk about the -1 sphere, which is just a shift. It's whatever information, you just shift the whole thing by. Yeah.
Okay, no other questions or speakers.